Download this code from codegive.com, link in the description below. OK, let's dive into the world of load balancing in multi-llm, large language model, setups. This is a crucial technique for building scalable, reliable, and cost-effective applications powered by these powerful models. Introduction: Why load balancing for LLMs? As LLMs become more integrated into various applications, relying on a single model instance can quickly become a bottleneck. Here's why load balancing is essential. Scalability. A single LLM instance has a finite capacity. When demand exceeds that capacity, users experience slow response times or errors. Load balancing distributes the workload across multiple LLM instances, allowing your application to handle a higher volume of requests without degradation. Reliability. High availability LLM servers can experience downtime due to maintenance, hardware failures, or software bugs. Load balancing ensures that if one instance goes down, traffic is automatically routed to healthy instances, minimizing service interruption. Resource optimization. Load balancing can distribute requests to different LLM instances based on their current load, hardware capabilities, or even cost. This ensures that you're making the most efficient use of your resources. A/B testing and canary deployments. Load balancing allows you to direct a small percentage of traffic to a new LLM version or a different model altogether. This is ideal for testing new features, evaluating performance improvements, or comparing different models in a real-world setting. Cost optimization. Different LLMs have different pricing structures. Load balancing allows you to route requests to the most cost-effective model based on the request's complexity and required performance. 2. Architecture. A typical multi-LLM setup with load balancing. Let's visualize a common architecture. Client applications. These are the applications, web apps, mobile apps, backend services, that need to access the LLMs. They send requests, typically over HTTP or gRPC. Load balancer. This is the central component responsible for distributing incoming requests across the available LLM instances. It monitors the health of each instance and makes routing decisions based on a chosen algorithm, explained below. Common load balancers include NX, HA proxy, cloud-based API gateways, example AWS API Gateway, Azure API Management, Google Cloud API Gateway, and specialized LLM routing tools. LLM instances. These are the individual servers or containers running the LLM. Each instance hosts a copy of the model and provides an API endpoint for processing requests. You might have multiple instances of the same model, or instances of different models. LLM server. This is the software that hosts and serves the LLM. Popular choices include Fast API /Flask, Python simple and flexible for building custom LLM APIs. Triton Inference Server, NVIDIA optimized for high-performance inference, especially on GPUs. Rayserve. A distributed serving framework well-suited for LLMs. LLM. This is the actual pre-trained large language model, example GPT-3, Llama 2, Falcon, Palm. 3. Load balancing algorithms. Choosing the right strategy. The load balancing algorithm determines how requests are distributed. Here are some common algorithms. Round robin. The simplest algorithm. Requests are distributed sequentially to each LLM instance in a circular fashion. Easy to implement but doesn't consider instance load. Weighted round robin. Assigns a weight to each LLM instance. Instances with higher weights receive a larger proportion of the traffic. Useful when LLM instances have different hardware capabilities. Least connections. The load balancer sends requests to the instance with the fewest active connections. Tries to balance based on actual load. Least response time. The load balancer sends requests to the instance with the shortest average response time. A more sophisticated approach that directly targets performance. Requires monitoring response times of each instance. IP hash, source IP hashing. The load balancer uses the client's IP address to determine which LLM instance to route the request to. This ensures that requests from the same client are always routed to the same instance, which can be useful for maintaining session state, though LLMs are generally stateless. URL hash, consistent hashing. The load balancer uses the URL or a specific part of the URL to determine which LLM instance to route the request to. This ensures that requests with similar URLs are always routed to the same instance, improving cache hit rates. Adaptive, dynamic, load balancing. The load balancer dynamically adjusts its routing decisions based on real-time metrics such as CPU utilization, memory usage, queue length, and response time. This is the most sophisticated approach but requires more complex monitoring and configuration. 4. Health checks, ensuring LLM instance availability. Health checks are critical. The load balancer periodically probes each LLM instance to determine if it's healthy. If an instance fails a health check, it's removed from the rotation until it recovers. Simple health checks. The load balancer sends a basic HTTP request, example a get/health endpoint, to the LLM instance. A successful response, example HTTP status code 200, indicates that the instance is healthy. Deep health checks. The load balancer sends a more complex request that tests the LLM's functionality, such as generating a short text snippet or answering a question. This ensures that the LLM is not only running but also functioning correctly. Code examples, setting up load balancing with llms and HA proxy. Here are examples using two popular open-source load balancers, llms and HA proxy. These examples assume you have multiple LLM instances running, each with its own IP address and port. llms configuration. Explanation. 1. Upstream LLM_cluster * defines a group of LLM servers. 2. Server LLM1.example.com 8000 * specifies an individual LLM instance, its IP address or host name, and port. 3. Weight equals 5 * assigns a weight to the server for weighted round robin. 4. Max_fails equals 3 fail_timeout equals 30 s * configures health checks. If a server fails 3 consecutive health checks within 30 seconds, it's marked as unavailable. 5. Proxy_pass http://llm_cluster * tells llms to forward requests to the LLM_cluster upstream group. 6. Proxy_set_header * sets headers to pass information about the client's original request to the LLM servers. 7. /health endpoint * this is the endpoint the load balancer uses to perform health checks. Important * you need to implement a /health endpoint in your LLM server, example using FastAPI or Flask, that returns a 200 OK status if the LLM is healthy. HA proxy configuration. Explanation. 1. Frontend HTTP_frontend * defines the frontend that listens for incoming HTTP requests on port 80. 2. Default_backend LLM_backend * specifies the backend to which requests are forwarded. 3. Backend LLM_backend * defines the backend, which is the group of LLM servers. For balance round robin asterisk sets the load balancing algorithm, example round robin, least con, least RESP. 5 option HTTP/CHK get/health asterisk configures health checks. HA proxy sends a get/health request to each LLM instance. 6 HTTP check expects status 200 asterisk expects an HTTP status code of 200 for a healthy instance. 7 server LLM1 8000 wait 5 check inter 5's fall 3 rise 2 asterisk defines an LLM server. Asterisk LLM1, a name for the server, can be anything. Asterisk LLM1.example.com 8000, the server's IP address or host name and port. Asterisk wait 5, the server's wait for weighted round robin. Asterisk check inter 5s, the interval, in seconds, between health checks. Asterisk fall 3, the number of failed health checks before marking the server as down. Asterisk rise 2, the number of successful health checks before marking the server as up. 6. Code example, implementing a simple LLM server, fast API. Explanation asterisk. 1 Fast API asterisk a modern, fast, high-performance, web framework for building APIs with Python. 2/health endpoint asterisk returns a 200 OK status with the model ID. Essential for health checks. 3/generate endpoint asterisk this is where you would integrate with your LLM. 4 time.sleep, 2, asterisk simulates the processing time of the LLM. Replace this with your actual LLM inference code. 5 error handling asterisk simulates an error if the prompt contains the word error. 6 Unicorn asterisk an ASGI server used to run the Fast API application. How to run the LLM server asterisk. 1 Install Fast API and Unicorn asterisk pip install Fast API Unicorn. 2 Run multiple instances asterisk open multiple terminal windows and run the server in each window, optionally setting a unique model underscore ID environment variable for each instance. 6. Advanced load balancing techniques for LLMs. Asterisk context-aware routing asterisk route requests based on the content of the prompt. For example, route requests requiring factual knowledge to a model trained on a large knowledge base, or route creative writing prompts to a model optimized for creative generation. This requires parsing the prompt and implementing routing logic in the load balancer or a separate routing layer. Asterisk latency-based routing asterisk dynamically route requests to the LLM instance with the lowest latency. This requires continuously monitoring the response times of each instance. Asterisk cost-based routing asterisk route requests to the most cost-effective LLM based on the request complexity and pricing structure. This requires estimating the cost of each request and comparing it across different models. This is especially relevant when using commercial LLM APIs. Asterisk queue management asterisk implement a queue in front of the LLMs to handle bursts of traffic and prevent overload. This can be done using message queues like RabbitMQ or Kafka. Asterisk caching asterisk cache the responses from the LLMs to reduce the load on the servers and improve response times. Be careful about caching sensitive or dynamic information. Asterisk model specialization asterisk use different LLM models for different tasks. For example, one model for summarization, another for translation, and another for question answering. Load balance requests to the appropriate model based on the task. Asterisk rate limiting asterisk implement rate limiting to prevent abuse and protect your LLM infrastructure from being overwhelmed. 7. Monitoring and observability. Asterisk metrics asterisk collect metrics such as request volume, response time, error rate, and resource utilization, CPU, memory, GPU, for each LLM instance. *logs collect logs from the LLM servers and the load balancer to troubleshoot issues and identify performance bottlenecks. *tracing use distributed tracing to track requests as they flow through the system, from the client application to the LLM instance and back. *alerting set up alerts to notify you when critical metrics exceed predefined thresholds. 8. Cloud-based load balancing solutions. Cloud providers offer managed load balancing services that simplify the deployment and management of load balancing infrastructure. AWS Elastic Load Balancing, ELB, Application Load Balancer, Network Load Balancer, Classic Load Balancer, API Gateway. Azure Load Balancer, Azure Application Gateway, Azure API Management. Google Cloud Cloud Load Balancing, API Gateway. These services often provide features like automatic scaling, health checks, and security features. 9. Challenges and considerations. Cold starts. New LLM instances may take time to load the model and warm up their caches, leading to initial latency spikes. Use warm-up requests to preload the model and populate the cache. Model consistency. Ensure that all LLM instances are running the same version of the model or that you have a strategy for handling version differences. Data consistency. If the LLMs rely on external data sources, ensure that the data is synchronized across all instances. Cost. Consider the cost of running multiple LLM instances and the cost of the load balancing infrastructure. Complexity. Load balancing adds complexity to your system. Carefully plan your architecture and choose the right tools and techniques. State management. LLMs are generally stateless, but if you need to maintain session state, consider using sticky sessions, IP hashing, or a shared session store. LLM specific load balancers. There are emerging tools and frameworks that are specifically designed for load balancing LLMs, taking into account the unique characteristics of these models, example long processing times, memory requirements. Look into those if you are building a large-scale LLM application. Dynamic scaling. Implement auto-scaling to automatically adjust the number of LLM instances based on the traffic demand. This requires monitoring traffic and scaling up or down based on predefined thresholds. Conclusion. Load balancing is a vital technique for building scalable, reliable, and cost-effective applications powered by LLMs. By distributing traffic across multiple LLM instances, you can improve performance, increase availability, and optimize resource utilization. Choose the right load balancing algorithm, implement health checks, and monitor your system to ensure that your LLM infrastructure is performing optimally. As the field of LLMs continues to evolve, new load balancing techniques and tools will emerge, so stay up to date on the latest developments. Good luck.